The next topic we're going to discuss is similarity of matrices. Suppose we have two matrices, A and B, and they're both n by n matrices, so they're the same size and they're square. We say that the matrix A is similar to B if there exists a non-singular matrix Q, that means an invertible matrix Q, such that A is equal to Q inverse times B times Q. So if you can find a matrix Q that's invertible and you multiply B by Q inverse on the left and Q on the right, and you get A, then we say these two matrices A and B are similar. Let's talk about some properties of similar matrices. The first property is that A is similar to itself. Why is that? Well, the matrix A can be written as the identity matrix, which is also n by n, times A times the identity matrix. But the identity matrix, its inverse is the identity matrix. So A is equal to I inverse times A times I. So every matrix is similar to itself, any square matrix. The second property is if A is similar to B, and B is similar to a matrix C. These are all n by n matrices. Then A is similar to C. How can we prove that? Well, since A is similar to B, we know there exists a matrix Q that's invertible, such that we have this property. But at the same time, B is similar to C. So there exists another matrix. It may not be Q, we could call it P, so P inverse CP, where P is invertible, because B is similar to C. Well, since right here I have a B, and here I have a B, I can substitute this in for B, and I get A is Q inverse times P inverse CPQ. And I can rearrange these parentheses because we know that matrices are associative under multiplication. So A is Q inverse P inverse. Let's put those in parentheses. C PQ. But look at this thing right here. This is PQ inverse. We already know that P and Q are invertible. And here we have Q inverse P inverse, which is exactly what we get when we take the inverse of two invertible matrices. So you can see that A is similar to C. We also have the property that if A is similar to B, then B is similar to A. Why is that? Well, if we assume A is similar to B, then we have A is equal to some invertible matrix Q inverse times B times Q. But since these are invertible, we can multiply the left side of both sides of this equation by Q. So we get QA is Q, Q inverse BQ. And this is just the identity matrix. So we get QA is the identity times B, which is just B times Q. But now I can multiply on the right side by Q inverse. And that's the identity matrix. So now I have that QA, Q inverse is B. Let's flip this just so it looks a little bit nicer. QA, Q inverse. I just put this on the left side and this on the right side. But notice that the inverse of Q inverse is Q. So then B is Q inverse inverse, A Q inverse. So now we see there exists an invertible matrix, which we're calling Q inverse, that the inverse of it goes here and the matrix goes here, and we get B. So B is similar to A. These three properties make up something called an equivalence relation. The first property here is called the reflexive property. Maybe you've seen this in an abstract algebra class. This is the reflexive property. This is called the transitive property. And this one is called the symmetric property. And if you have all three of these, it's called an equivalence relation. So similarity is a type of equivalence relation. What are some other properties? This one's interesting. If A is similar to B, then A raised to a power K, let's let K be greater than or equal to 0. That is similar to B raised to the same power. Let's prove that. Well, if A is similar to B, we know that A is equal to some invertible matrix, Q inverse times B times Q. But what happens if we raise A to the power K? Well, A to the power K is Q inverse B Q to the K, which tells us that A to the K, let's expand this. This is Q inverse B Q, Q inverse B Q, Q inverse B Q, and we keep doing this K times. Q inverse B Q. So let me write it like this, or I say we write this K times. Now we can't just flip matrices. Remember that multiplication of matrices is not commutative. In other words, if we have two matrices D and E, if we multiply them, that's not necessarily E times D. But we do know that if we have something like D, E, F, and we put D and E in parentheses, this is equal to D, E, F, like this, with E and F in parentheses. So multiplication of matrices is associative, but it's not commutative. The reason I bring that up is we can drop all of these parentheses and then place them around the Q and the Q inverse. Okay, so every time we have a Q times a Q inverse, that becomes the identity matrix. And what we're going to be left with is A to the K is equal to, well, we still have this Q inverse here. And we're going to have, because we wrote this K times, we're going to have KB, so B to the K. And we're going to be left with this Q as well. So you can see that A to the K is similar to B to the K. This is actually something very important, because if you have a matrix that you want to multiply by itself K times, let's say it's a really big matrix and it's really hard to do that in your, let's say you have some kind of computer program, it's taking a lot of time, but you know that it's similar, let's say, to a diagonal matrix. So if you have a diagonal matrix, let's say the matrix looks like something like this. And if you know what this Q inverse is, and this Q is, if you want to figure out what A to the K is, well, then you just have to multiply this diagonal matrix K times. And a diagonal matrix, when you multiply a diagonal matrix with itself, all you're doing is you would be multiplying these entries by themselves. So in other words, this would be equal to 1 to the K, 2 to the K, 3 to the K, and so on. So it's a lot quicker to calculate a power of a diagonal matrix, or let's say you have an upper triangular matrix or a lower triangular matrix. If you know that your matrix that you want to actually calculate raised to a power is similar to a diagonal or lower upper triangular matrix, if you can calculate that, and if you know what Q is, you can just calculate this part and then multiply by Q inverse and Q, and you can get the actual matrix you were interested in. Okay, let's look at one more interesting property, which is the identity matrix I, which we're going to say is n by n, is only similar to itself. In other words, there's no other matrix, A, that's similar to the identity matrix. Why is that? Well, obviously, I is equal to I inverse I times I. So I is an invertible matrix that you can see that is, so I is similar to itself because you can put I here and here and you get I, so no problem there. But let's say there's some A that's n by n that's not equal to the identity matrix. What I'm saying is I is not similar to A. It doesn't matter what you choose, I'm telling you, I'm promising you, there's no matrix other than the identity matrix that the identity matrix is similar to. Why is that? Well, let's prove it. And we're going to prove by contradiction. So what we're going to do is we're going to assume I is similar to some matrix A, this n by n, and it's not equal to the identity. Well, that means there exists a matrix Q that's invertible such that I is equal to Q inverse AQ. So what can I do with this? Well, this matrix is invertible, and I can multiply on the left by Q, and I can multiply on the right by Q inverse. So let's do that. So Q inverse I is equal to AQ because I'm getting rid of this. If I multiply on the left, this becomes the identity matrix. And then I multiply on the right, so I get Q inverse I. Oh, sorry, let me say that again. Actually, it'd be better if I write it out. I'm going to multiply by Q on the left, so Q inverse AQ. This becomes the identity, so we have Q times I is A times Q. And now we're going to multiply on the right by Q inverse, so we get QI Q inverse is A Q times Q inverse, so that becomes the identity. And we get Q times I times Q inverse is A. But what happens on the left-hand side? Anything times the identity is itself. So if we multiply these two together, we get Q, and we bring this Q inverse down. But then Q times its inverse is the identity. So we get that the identity is equal to A, which is opposed to what we assumed in the beginning. So we have a contradiction. Great. So the next thing I want to talk about is I want to bring similarity back to linear transformations. From now on, I want you to think of matrices as linear transformations. So if you have an n by n matrix, let's say A is a n by n matrix. For any matrix that you can think of, you can associate a linear transformation that takes Rn into Rn. Or you could have another vector space other than Rn, but have dimension n, and a vector space W that has dimension n. So there exists a linear transformation such that you have a basis for Rn, and that same basis or some other basis is equal to A. So there's some linear transformation out there and a basis that if you plug it into the linear transformation and write it in terms of another basis for the same space, you get the matrix A. The reason I am bringing this up is because if we have a linear transformation L that takes Rn into Rn, and let's say we have some basis B equal to, let's call it B1, B2, all the way to Bn. And let's say A is equal to this linear transformation where we plug in each one of these basis elements into our linear transformation and write it in terms of those basis elements. And then let's say we have another basis. Let's call this basis B hat. And I am going to say that what's inside this basis, let's give everybody a hat. So remember that a vector space has infinitely many different bases. They all have to have linearly independent vectors that span our vector space, which here is Rn. But we can come up with as many bases that we like. So let's say we take that same linear transformation, plug in this basis, and write it in terms of this basis. And let's call this matrix B. Then A is similar to B. Now this is very important. And there's a matrix Q So there exists a Q that's invertible such that A is equal to Q inverse BQ. Now what do you think this matrix Q is? Well, A is this linear transformation from B to B, and this matrix B is equal to this linear transformation where we're taking the basis B hat into B hat. Q is our change of basis matrix. So maybe we can put that one in red. Q, well, remember how we set this up? We take this into this one, and when we did things with change of basis matrices, like if we had I B hat times some vector in B hat, we got the vector in terms of this basis, remember? Because we said that we would cross these out and we would be left with this. We're going to have something just like that. Here I'm going to put, I want to get rid of this basis, so I'm going to put B, that's the basis I want, comma, B hat, and here I'm going to put B hat, comma, the basis I want, which is B. Why that works is because these cancel out, and I'm left with, you can think of I times L as L, and L times I as I. So then this simplifies to L with this basis and this basis. Isn't that interesting? So if you take a linear transformation and you write the matrix associated to the linear transformation with respect to one basis, and then take that same linear transformation, write it with respect to a different basis, then those two matrices that you built are similar to each other. And they're similar with the invertible matrix Q being the change of basis matrix. Okay, I want to show you an example of this. I've actually worked out a whole problem for you, and I think I'm going to do something similar to this for maybe a group project. So here's my example. I have this linear transformation L that takes R3 to R3. I'm going to talk about it for a second and what we want to do, and then you should copy it down, maybe even try it on your own. I've skipped some steps for you to work through for your project, but yeah, this is really interesting. So let's look at it. We're taking R3 into R3, and what we're going to do is, for any vector, we know that it has three pieces, x1, x2, x3, and L is going to send x1 right here to x1. Then I'm going to, for the second entry, I'm going to add these two, and then for the third entry, I'm going to multiply the third entry in the domain by 2. Okay, so one thing you could do is check that this is actually a linear transformation. It is. We're not going to do that, but you could do it. And then I chose two bases. So the first basis that I chose was just the standard basis, and I called this B in blue, 1, 0, 0, 0, 1, 0, 0, 0, 1. The second basis I chose was 1, 1, 1, 2, 0, 0, 0, 1, negative 1. Now, to show that this is a basis, you would have to show that they span and that they're linearly independent. However, we know the dimension of R3 is 3, so we really only have to show one of those. Either it's linearly independent or it spans. It's easier to show it's linearly independent, and you can do that if you'd like to show that this is linearly independent. Okay, but I'm not going to show that. I'm just assuming that at this moment. What I want to do is I want to show that this matrix, L, the matrix with respect to this linear transformation L, where I plug in this basis here, B, and then when I plug it into L, I write it in terms of those basis elements. I want to show that that matrix is similar to this one, which is taking that same linear transformation, plugging in the basis elements of this basis, and then writing them in terms of this basis. So how are we going to do that? Well, my first step is actually just to calculate this matrix. And then once I calculate that matrix, we could calculate this matrix. So let's do that. Let's calculate this matrix. So what do I need to do? I need to take this vector, plug it into here, and see what I get. Take this one in, plug it in, see what I get, and then this one. And then once I do that, each one of those solutions, I write it in terms of these basis vectors. So that's what I did. I plugged in 1, 0, 0, 0, 1, 0, 0, 0, 1. Look and see what I got. And then I write it in terms of the standard basis. And because it's in terms of the standard basis, all I have to do is actually just write those 3 columns here. So that's the easy one. Now I'm going to do the same thing. I'm going to take the other basis, 1, 1, 1, 2, 0, 0, 0, 1, negative 1, and I'm going to plug it into the linear transformation. Okay, I believe that the linear transformation was x1 plus x2 and 2 times x3. Okay, so if you plug this in, you get 1 plus 1 is 2, and then 2 times this is 2. You can see that you get 2 plus 0 is 2, and then 2 times this. And then finally 0 plus 1 is 1, and then 2 times this is negative 2. So once you figure out these columns here, what you get when you plug in the basis vectors, what's the next step? You need to write each one of these vectors in terms of this basis. So you write 1, 1, 1, 2, 0, 0, 0, 1, negative 2, because that was the original basis. This should be a negative 1. Sorry about that. And see, these were the original basis vectors. And then you try to figure out what you need to multiply each one of these vectors by to get 1, 2, 2. Now how you can do that is you can put all of these vectors into an augmented matrix with the vector you want right here and get it in a reduced row echelon form. If you do that, you'll see that you get 2, negative 1/2, 0. And that's how I got these 3 numbers. And then this 2, negative 1/2, 0 is what goes here. And then I do the same thing for this 2, 2, 0. And then for this 0, 1, negative 2. So for the 2, 2, 0, I would get this column. And then for the 0, 1, negative 2, I would get this column. Okay, now we've found this matrix. What's our next step? We want to find this invertible Q such that the matrix with respect to L and this basis is equal to Q inverse this matrix with respect to this basis times Q. Okay, how do you do that? Well, to figure out the Q, you have to find this change of basis matrix. And I want to get rid of this basis and make it this basis. So to get rid of this B and get the new B, so get rid of this B hat, I have to put the B hat here and the B here, and then put the B hat here and just the regular B here. Okay, so one of these is actually really easy to solve, and that's because we're using the standard basis. The one that's easy to solve is this one. Why is it easy to solve? Well, what do? We take our basis and we write it in terms of the standard basis. So what is the standard basis? 1, 0, 0, 0, 1, 0, and 0, 0, 1. So we're taking this basis and writing in terms of the standard basis. Well, that would just mean that I put these as my columns in the matrix, because 1, 1, 1 is one of these, one of these, one of these. 2, 0, 0 is two of these, 0 of these, 0 of these, and so on. So that one is really easy to figure out. And so I've written it right here. 1, 1, 1, 2, 0, 0, 0, 1, negative 1. The other one is a little more complicated to figure out. You're putting the standard basis in, and you're writing it in terms of this basis here. So the standard basis is 0, 1, 0, 1, 0, 0, and 0, 0, 1. And you want to write each one of these in terms of this basis, which is 1, 1, 1, 2, 0, 0, and 0, 1, negative 1. And you can do that if you want to. Another option is to remember that these two matrices are the inverses of each other. So you can do exactly what you did to get this one, which is just a little more work, or you could just take the inverse of this matrix. So if you take the inverse of this matrix, now you can use a computer program to figure that out, or you could, use what we learned earlier in the semester to find the inverse. But once you have the inverse, then you see that so this matrix here goes here, and then this matrix, let me move it up, goes here. Maybe we can write it all as 1. Let's do that. Okay, so I claim that L in terms of B is equal to 1, 1, 1, 2, 0, 0, 0, 1, negative 1, times the matrix we found for L B hat, which if I scroll up, I'm going to copy this, put it here, oops, and then we multiply by this matrix here. So if you multiply these three matrices together, what you should end up with is this matrix right here. Technical difficulties here. Okay. Done. Isn't that interesting? So you have this matrix that multiplying it by these two matrices will guarantee that we get this matrix. And you could even put this in the calculator and double check it. But this is what you'll get. And we're done.